Okay, so as usual I'm having issues with the projector. It's not even displaying the regular computer, so that's okay. Today's topic is going to be mostly a couple of topics, new topics, which are small, and then we'll try to go over some review of all the previous few lectures. So previous 5 lectures, we'll review some of the topics. And if you have questions, I don't know if you have already started preparing, but if you have questions, then we can address them during that time. Okay. So as you know, we have the exam on 3rd, right? Which is a Saturday, so it's during the class hours itself. The format of the exam is going to be a few questions, I think about 6 to 10. The number of points is basically proportional. It's all equal point questions, and each lecture has a bunch of sample questions, right? So the exam questions would follow a similar pattern, and they may not be the same. So don't bank on the fact that they will be the same. That would be very bad. Then you will not do well. Yeah. So the exam questions would be similar in terms of difficulty. You know, you want to understand what's the difficulty level, right? You don't want to get bombarded with some derivation. So. Yeah. Yeah.
So in this exam, they don't have proving.
No proofs. Probably no proofs, but yeah, but when you write the answers, you should strive to use some technical phrases and words. I think that's what in the previous versions we saw that people were using English descriptions of things that they know. You know, they know what it is. It's just that they're just using English description, which sometimes get penalized. So try to stick to a little bit of statistics language. Like if you're describing the mean, then just use a mean. Don't say sum of all these numbers and then I'm going to divide n and something like that. But at the same time, sometimes you may misuse a statistical word, which is even worse. So if you are in doubt, just stick with it's better to get partial points on something that you know, rather than using an incorrect word. Okay, that will signal to the grader that you are actually completely misunderstanding something. Okay. What's happening here? Oh, that's a good question. So what's written in the syllabus? Does it say you can bring in cheat sheet or no?
Yes.
Okay, so yeah, you are allowed to.
How do we have no idea what to put on that? Cheat sheet like a page?
Yeah, it's a page, yeah. So no computing devices, I think. Let me just... yeah, I mean, if you are, some real estate left, so you should just use it.
You can just give like a couple of examples, because right now it's very confusing. We need to concentrate on what we did in the class, mostly derivation type of things.
There's not much derivation that we did, right? There's a couple of derivations that we did, that's all. And those were just calculus based, right? I don't remember any derivations that I did. I think I only did some, the linear regressions, optimal solution. But I'm not going to ask that for sure. But that doesn't mean you don't remember at least the final solution. And I should know the final solution. Sorry, I'm just looking at the...
So is it one cheat sheet or multiple cheat sheets?
I think so. I'm just seeing the syllabus page, and it says one regular sized an A4 sheet or a letter sized sheet of paper. Yeah, you can ideally handwritten. That's something I'm just saying right now. Ideally it's handwritten. So it's not just somebody types it out and copies it for the rest of the class. I mean, if I see that, I'll just increase the grading harshness. So No, I mean if you haven't put effort there, then means that you have put more effort in reading stuff. So, which means that I should appropriately scale up. So, okay, so it's that projector is on, but it's not displaying anything. Let's see. And I think the LTS is closed now anyway, so can't even take recourse. Call them out, fix this. Yeah, it's fine. I think we have done board-based things. No, I think it's basically saying that the projectors are off. Okay. So any other questions about the exam? It's fine, right? So the content would be the first 6 lectures. So 6th one is today, and today I'm going to cover a couple of very quick topics and then get to some review. Okay. Okay. So let's see. So I'm going to start from here. So most of the classes seems to be centrally located. If it flashes, just let me know. It's done. Okay, I hope it turns on. Okay, so today we'll just there was one assignment question. So have you already submitted assignment 2? So it's due tomorrow? Tonight. And there was a question 3.6 from the first book.
Yeah.
So it's basically related to interpreting loss functions as relating loss functions as a general principle called the maximum likelihood estimation. So how many of you have seen maximum likelihood estimation in any of the courses before? So which courses have you seen MLE?
I'm taking the revenue management course.
Okay.
So over there, they are introduced this, and one of the courses I took last semester, 570.
Yeah. So people who have taken 570 have looked at maximum likelihood estimation. I mean, some simple examples of MLE problem. Okay, so today we're going to look at maximum likelihood estimation, and the second thing is Bootstrap. Both are, so MLE is is a technique that you should know because it will put you at ease in terms of looking at all these variety of methods. Many of them are very simply motivated by assuming some assumption on the joint distribution of x and y, and then just maximizing likelihood. So I'm going to describe what it is. Some of you may already know this, so the first topic will be slightly easy. Second topic, Bootstrap is a very practical tool to get bands around your predictions. Okay. These are not, so I said bands and not intervals because confidence bands is roughly the phrase used for Bootstrap-based bands or uncertainty bands, and confidence intervals is like the more traditional. When people say confidence interval, they probably mean more assumptions and more traditional, like something related to, let's say, linear regression. Okay, where you make some assumption about data and therefore something called confidence interval makes sense. Okay. So we'll use confidence bands. So there's a difference between bands and intervals. Let's not worry about intervals at all in this course. So Bootstrap is a very practical thing you can use for your projects or for your database processes. So the first topic is essentially a review for some of you. very cool app that I wanted to demo, and the internet is not working. So those of you who have your laptops or have access to the notes, it's already posted, right? Have a look at a link on the first example. It's a very cool link, especially you can play with your webcam, generate real-time data. So generate data on the fly, which are image data, and then you can do like multi-class classification. Okay. There they actually use some other prediction models, so not the logistic regression or LDA that we saw last time. They are classification models, but they kind of stick with linear decision boundaries, or maybe QDA looks like quadratic decision boundaries. The models that these guys use are within the family of what I call neural networks. It's just a nonlinear family of models for, again, mapping some input variable x to qualitative variable g, right? So it's just nonlinear, that's all. And because it's nonlinear, the way to estimate the best parameters for that model happens to be, involve some phrases like backdrop and stuff like that, gradient descent and all that. But have a look at that link. I hope it still works from previous version of the course. Okay. So previously we were just focusing on mapping x to y and getting a function f, right? So this was supervised learning, and let's take the particular example, which was that residual sum of squares. Was basically sum over I 1 to m of yi minus that's a beta transpose xi squared. And in the homework, which you're going to submit soon, you were asked to kind of relate, actually not just residual sum of squares, ridge regression to ridge regression to a Gaussian interpretation. Basically, a product of two Gaussians where you have a trion on beta and you have a likelihood model, and then you get a posterior. So I'm going to explain what that is. So let's not worry about ridge specifically. So what is likelihood of data? So what is likelihood? Likelihood is just the alternate name for a probability of something, okay? And the probability of something is the probability of you observing some data. So let's say, so in supervised learning we have two sets of variables that we distinguish x and y, but you really don't have to do that. You can consider z as x comma y, where maybe you just added y as a additional coordinate of your input variable. So basically I have p-dimensional variable here, maybe y is one-dimensional, I just concatenate them and just call this new variable p plus one-dimensional, which is z. So we don't really have to think of input and outputs anymore. Okay. For a general variable z, likelihood is going to be just the probability of observing z1 to zn. Okay. Let's say I have n observations, then all I'm saying is this is a variable, this is a random variable because I just in fact random vector because it's p plus one dimensional, and all I'm saying is what is the probability of observing these n realizations of this random vector, right? And likelihood is just the probability of this under some model. So generally you subscript p with theta. So this is the probability of observing these n data points, right, under a model. Okay. And let's, for example, not worry about prediction models. Just think of how to understand likelihood problems. So I'll give you a very simple example. This is the example of z being just binary. Okay. So let's say z is Bernoulli with parameter p. All I'm saying is z is the outcome of a coin toss. If it's heads, let's say z is 1, and if it's tails, z is 0. Okay. So z is a random variable with this distribution. So this distribution means the parameter theta is just one dimensional and it's p. Okay. And so given this, what is the likelihood of observing n different realizations of z. Okay. Another implicit assumption that we can make here is that me flipping a coin now has nothing to do with me flipping a coin in the next index. Okay. In the sense these realizations are independent. Okay. Which means that let me focus on just the probability of, let's say, z1, or just the probability of theta with respect to z. So So what is the probability of let's say z1. Okay. Let's say capital Z1 is okay. Sorry, I should have said that. Okay, I'm going to use lowercase for the realization. So just a little z1 to zn. Okay. So this is just a trick to write it this way, but you'll see how it is. So it's probability that with probability p, it's going to be this, and with 1 minus p probability is going to be 1 minus z1. This is just succinctly writing, the probability that z takes a value little z is just this for the Bernoulli model. Okay, it's succinct because if you just substitute z is equal to 1 or 0, let's say z is 1, then this term is gone and it's just p. Probability of z is equal to 1 is p, and probability of p is equal to 0 is just 1 minus p. So it's a succinct way of writing it.
What is the p in this case? Probability?
P is this parameter, this theta in this Bernoulli model is going to be just this one-dimensional number, so scalar number, little p. Okay, I should okay, little p. Okay, let me just make it q. Doesn't matter. Right, and then and so you have this general form. Then all you're asking is what is the likelihood of my data? Then it's just a product of these guys. So okay, before we even take product, likelihood is generally I said it's a product distribution. It's a product of all these n realizations, and I'm saying product because I'm assuming independence. So this joint distribution, right? Capital Z taking a value little z1, capital Z2 taking a value little z2, and so on. It just boils down to, so this was the short form for product. Product is equal to pi I is equal to 1 to n of p theta of capital Z I taking a value little z I. Right. So capital Z I's are just copies of copies of this Bernoulli randomizer. We'll interpret it that way. Just copies. And so since there is a product of this, and we want to figure out. Typically, what we'll do with likelihood is you want to figure out the parameter. Okay. Given data, I want to figure out what is the best parameter that explains the data. As in that best parameter that gives the highest probability to the observed data. Okay. When I say explains the data, all I'm saying is this is likelihood for any theta. For any theta, actually any q. Q is the only parameter in this model. For any q, this is the probability assigned to observing little z I, little z1, let's say. I want to figure out that q which gives me the highest probability of observing little c1. And to do so, what happens is because there's a product, we like to work with log of this. So log of this likelihood. So typically, so we are trying to figure out the best theta that gives the highest mass to the observed observation, but instead of maximizing the likelihood itself, we'll maximize the log likelihood. So because we want to get to log likelihood, let's just take the log here itself to see how it looks like. So log of p theta is just z1 log q plus 1 minus z1 log 1 minus q. Okay. And I just skipped the bracket, but you can decide it. And so now let's get back to log likelihood. Log likelihood. for any parameter theta, and in this model the parameter is only one, q. Okay, it's just one number. Log likelihood is just going to be a sum over I is equal to 1 to n of zi log q plus I guess I can I is equal to 1 to n of 1 minus zi of log 1 minus q. I'm going in laborious detail because next class is going to be a delta shift. In the sense, we're going to kind of assume that you understand what this means. So this is log likelihood, and so we want to figure out, and the data is here. So this was a convenient notation so that we did not explicitly say whether zi was 0 or 1. That was the only nice thing here. And so now we want to maximize. So we want to typically, maximum likelihood estimation is just the problem of maximizing log likelihood of theta over theta. I can change theta. I want to maximize I want to figure out that theta which gives me this probability, or log of the probability. Okay. This probability has the highest mass for the observed data, and this number is the highest for the observed data. So, is the concept clear? You want to keep changing theta. For different thetas, you'll get different numbers here, right? The probability of observing this particular sequence of data. I want to figure out that theta which maximizes its probability of seeing data. The data is fixed, so that's not big thing, right? And so let's do MLE for this guy. And it's just going to be maximized over Q of this objective, right? This thing. So let me call this sum n1. Okay, it's just a sum of coins, yeah, so this is I is equal to 1 to n of zi. So this is a constant log q there. It's not there's no I index there. So I'm saying that the sum of I is equal to 1 to n, let me just call it n1. Okay. This sum is, so each of zi's is either 0 or 1. So this sum is also a number, right? I'm just calling it n1. That's all. And then so let's say n1 log q plus the second number turns out to be just n minus n1, right? Because I have n observations, either they are 0 or 1. So if the first sum is n1, the second sum has to be n minus n1. Okay. Is this a short form? You can retain the same thing, don't worry about it. If you're confused about n1s, then just copy the same thing. Log 1 minus q. And so how do you maximize something like this? It's an unconstrained, okay, it's not really unconstrained, so we want to ensure that q is between 0 and 1. Right? Q is the parameter. I mean, the parameter can only be between 0 and 1. So how do you maximize this?
Derivative.
Yes, I mean, if you're doing on paper, you just take derivative. If you don't know anything, you just try for every q value what this number is and figure out, like just to break the q interval 0 to 1 into pieces. Okay. Try q is equal to 0, q is equal to 0.1, 0.2, and so on, and figure out where the number is highest, and you get the q. Okay, that's just like just search, right? So yeah, here you can take the derivative, and here it's going to be n1 by q, right? Minus n minus n1 by 1 minus q. Right? The derivative of log is 1 by log x is 1 by x. So okay, so let's set the derivative equal to 0. Actually, you should check the second order condition that this is, take the second derivative and see the second derivative is, so what is the second order condition for maxima? Okay, you just need to ensure the second order condition is either positive or negative. Okay, I don't remember what that rule is. I mean, you can intuit it, but let's not worry about it. So you can see that the solution. Since we took the derivative, let's call this q hats. Okay. So n1 by q hat is equal to n minus n1 by 1 minus q hat. And so just do a change of just move things around. So it's 1 by q hat minus 1 is equal to n by n1 minus 1. Right? Or is it a font too small? Okay. and then so you have q hat is equal to n1 by n. Okay. It's just the sum of heads divided by the total observations, and that's kind of very obvious, right? This is what I did this derivation because we kind of glossed over in LDA. In LDA, we said the estimate for, so there were, LDA had some parameters, right? So LDA had some parameters. Yeah, the class probabilities, pi's, and I said class probabilities are just the count of number of times, if you have n observations in the data, then count the number of observations which have class J. Okay. Something like this. Remember, I don't know if you have seen the notes, but there was an estimate like this, and LDA had another estimate which was mu hat J. So J is a class. You are doing K class classification, right? And mu hat J was just the sum over xj's, xi's. I is equal to 1 to n, 1 by n. Wait, not 1 by n, but nj. So okay, this quantity, let's call it nj. Okay, the numerator. So let's say in 100 observations you have 10 observations which are class 1. Then pi hat 1 was just 10 by 100, right? So I'm just calling the numerator nj for simplicity, and mu hat j, the mean for the first class, let's say jth class, is just going to be 1 by nj sum over I is equal to 1 to n of xi, where it's not just okay, let me 1 by nj sum over I such that the class gi is equal to j of xj. What I'm saying is just take the subset of those observations which have exactly the jth class, and there will be x's corresponding to that. Take the average, and this is just average. Nj is exactly those number of observations. So this is just an average. It's just saying do per class averaging. Why was this a formula? There is if you remember, LDA has an explicit assumption about the class conditional probability of x given class G is equal to J was actually normally distributed. Normally distributed, Gaussian distributed are the same. Normally distributed with mean mu J and variance sigma, right? And we use sigma, and people got confused. Some people after the class said it's a bit confusing. You can use B if you want. It's because sigma also is like a summation term. Okay. We made some assumption like this, and in LDA, you are actually solving a likelihood problem, and the solution of the likelihood problem, just like for Bernoulli problem, turns out to be the best solution. Maximum likelihood estimate is just the count of number of heads divided by total observations. In the LDA situation, if you maximize the likelihood of LDA's likelihood of the data observed, x's and y's, x's and g's, then these are the MLE estimates. I mean, I just wrote two. There's another one which is for B hat, and there's a formula in the notes. It's just unwidely and doesn't give much interpretation. So, I mean, it's just a simple formula for estimating the variance of data, the covariance of data. Is this clear? Any questions? So this is the same as what MLE that you saw in 570, let's say, some of you, or revenue management.
Till you were doing the Bernoulli.
This is a template thing. I mean, this is what you do. So you just write down some probability. I mean, you can assume Bernoulli, you can assume normal distribution, whatever, and mostly it's going to be, you take the log of the likelihood. It's going to involve sums because you typically assume independence of observations. Because there's a product here, there'll be sums here. But whatever model you assume, you'll have some objective function, and then you'll need to maximize it. Okay. and in the in the assignment you do mode of the posterior. Okay? Mode of the posterior, or mode or mean of the posterior is like the maximum of, this is like the posterior log of the, okay. Yeah, so here, this problem, maximum likelihood estimation is a lot of maximization, but when you connect it back to loss functions that we look at, you just tack on a negative term. Okay, so then, so some of you who have done hopefully 3.6 know that if you think of normal distribution, there's a e to the power minus x minus mu square, and so there's a minus there. If you take a log, there's a minus term hanging in front of the exponent of the of your normal distribution, and maximizing a negative term is the same as minimizing the positive term. Okay, so that's the connection between. Okay, let me just let's not worry about rage, but let me solve a simpler problem. I mean, not solve, but like let's say, I think this interpretation I gave, or maybe gave very quickly. So residual sum of squares was just sum over yi minus x transpose beta I, x transpose I squared, right? So we are minimizing this. So minimize over beta, right? So this was without the probabilistic interpretation. This is what we introduced in first class, right? First lecture. But this I had connected, or if I did not, I'm going to repeat it for the next couple of minutes. This is basically related to this model where we are assuming y is beta transpose x. So these are capitals. These are actually input and output variables, plus another random variable epsilon, where I'm going to say not random, and epsilon is normally distributed with mean 0 and variance sigma square. Okay. I mean, assume. So this is what is without the probabilistic interpretation. We just wanted to minimize the squared error between prediction and true values, right? Qualitative observations, realizations. Here, if you assume this, then I've assumed something. The only thing I've assumed is epsilon is normally distributed. X is not random, so it's something, I'm not going to model it as a random thing. Then y is random because, it's a sum of two terms and one of the terms is random. Okay. And in particular, probability of y, okay, given y given beta transpose x is just normal distribution. So it's basically exactly equal to y equal to less than little y is square root 2 pi sigma e to the power minus y minus beta transpose. Let's say little x and little y are what we're looking at. Beta transpose x square by 2 sigma square. So all I did was substitute what is the random variable. Here it's y. What does it mean? It's mean. Because epsilon is 0 mean, y's mean is just going to be the first term, right? It's an offset. It's like a shift to a 0 mean random variable. So this is the offset that I'm writing here, beta transpose x. Okay.
Can you repeat this step one more time because I'm using capital Y at small y?
So whenever we write just probability of x, it's basically we're talking about probability. Its probability is always for the realizations, right? Probability of the variable taking a value, right? And this is a short form. This is the right way to talk about it. I mean, you don't have to write it in this messy notation. All I'm saying is probability of y is equal to little y. But y depends on this, and I said x is not random. Let's say it took a value little x. Then that's data. That's basically beta is beta transpose x is essentially some number that you know at this point. So if you know beta transpose x, then that's the mean, and that's it. This is just a definition of a normal distribution, one dimension. And then, so this is your essentially same thing as this, equivalent to this. The two parameters. Okay. Yeah, let's say the two parameters are, you'll see that sigma is irrelevant. The parameters here are sigma and whatever is parameterizing there's a beta that keeps appearing irrespective of any change x, right? In the sense of, let's say there was some other x, instead of x there was an x prime. Even there's a beta, so you can think of beta as a parameter. Right? It's just a loose interpretation. And then you're saying, how do I maximize this, log of this thing over my data? And because we assume each observation is independent, there's going to be a sum. So log of I is equal to 1 to n of this box, this is this probability. Maximize it over beta. Okay, and you can also maximize it over sigma. That's not very important. You'll see the sigma drops out, so that's why I didn't do it. Is this clear? So we wrote because we assume something about the random variables. So what exactly is the random variable y? It's exactly normally distributed with mean beta transpose little x.
Okay. This is also the probability density function if we assume that.
Yeah, this is the PDF. Yeah. This is the density function for y. Y is a random variable. This completely tells you what is the probability that takes little value y, what is the probability takes values within some interval, and so on. Right?
But is it going to be a cumulative probability density function, or will it give the value at a certain point?
Okay, so in this class, so this gives you a value at a point. Okay. In this class, we'll loosely use distribution to only. In technical, more technical classes, people use distribution to talk about CDFs, cumulative distribution functions. But in most of our discussion throughout this class, we'll loosely use distribution to say just probability density functions. So CDFs are nice, but we will probably not encounter them in this course. Okay. So mostly, when I say distribution, I'm talking about either probability mass function. So this is a probability mass function. This is actually takes two values, q and 1 minus q. They sum to 1, and takes value 1. Random variable takes value 1 with probability q, takes value 0 with probability 1 minus q. Right. So it's a probability mass function. There's a probability density function, and here. So assuming this assumption about random variables, this is the density function that we got of data. So now we have data and n observations yi and xi, right? And so we know that probability of y taking a value little y, little yi, and given xi, given because xi is not random, is just this yi minus beta transpose xi. You just substitute that, and you get one number. And now you're asking, what is the best beta that gives the highest probability of observing little yi? Okay, because xi is not anyway not random, so it's not part of it. And taking log is just a trick. You don't have to take a log. Then you have to stick with products. Okay. Log of a product, log of a times b is log of a plus log of b for any ab. I mean, not really any, because a and b have to be positive, but those are just facts. So you take the log, and so what is the log of this term? So log of this term has some coefficient here, right? Doesn't involve beta, so let's not worry about it. So log of this term is, let's think of the coefficient times another term, so two terms, right? And we know that log of a times b is log of a plus log of b, right? But a has nothing to do with beta, so it's like, it's a constant, it doesn't matter. Which beta I pick, it doesn't matter, it's going to give me the same value. So let's ignore the coefficient here, or 1 by 2 sigma square, 1 by square root 2 pi sigma, let's ignore it. This guy, log of e to the power something, what is it?
It's the term.
Just the term itself, because log and e to the power something, they are what I call inverse of each other. Okay. So what I'm saying is you'll essentially get a maximization of beta of log of this. This anyway will be shifted, there's some constant, and log of e to the power something is minus yi minus beta transpose xi square. Again, there is a 2 sigma square, and I said logs turn things into sums, so let's put a sum here. I put 1 to n. Okay. This is fine. Is it too low for you guys? I mean, there is this whole monitor and all. Is this fine? Everybody can see this? You can see this? Okay. I don't know how. Okay, so this is again doesn't depend on beta, it's like a scaling, right? Sigma. And then you can see that maximizing this is the same as minimizing the non-negative version of this, and which is residual sum of squares. Okay. So this is just a principle, one way of looking at loss function. So why did you arrive at this loss function? At least you can say, if I assume some assumptions like this, then maximizing, my maximum likelihood estimation problem just is the same as minimizing residual sum of squares. Right. Any questions about this part? And was the question 3.6, did it say map estimation? No. Okay. So just a quick aside, or not as an aside, but so there is a version of this problem. In maximum likelihood estimation, we're saying what is the likelihood of data, and so for us it's actually the parameter is just a fixed unknown number, and we just need to find the best number, or okay, in this case it's not a number, but it's just a p-dimensional vector. What is the best p-dimensional vector that maximizes the likelihood? There is a interpretation which is called Bayesian interpretation, where the parameter is also a random variable. Okay, so this is Bayesian slash maximum a posteriori estimation. So MAP. Okay. So you can think of theta as a random variable. Okay. Theta in this case is beta, in this case is q. Okay. And let's think of the Bayesian issue. Bayesian problem is kind of easy to understand. When I say Bayesian, they don't want to think of any numbers as constants. They want to think of everything as random variables. So here, one of the key things there is Bayes' rule. So you can find the probability of theta given data as the probability of, I'm just writing loosely as data, as probability of theta divided by, okay. This is kind of resembles Bayes' rule if you think of theta as a, event A, and second part is B. So this roughly is actually true as well. So when I say data, you can think of this as z. Okay. So z is a random variable. So probability of theta is a random variable given z. It's probability of z given theta times probability of theta divided by probability of z. Okay, for example. And the full Bayesian version of the problem is you assume some. So this we anyway assume. Given theta, what is the probability of z? Is Bernoulli. Okay. Given q, how does z behave? Given q, how does z behave? It's Bernoulli. Okay, in this example. So this is the same component as in MLE, right? but there is this additional new component. This is the second component which is new, which is called a prior, and you've probably heard this before. So this is a likelihood, just as before. This is called a prior. Okay, likelihood times the prior gives you what is called the posterior on theta. So the posterior distribution is the distribution on theta. So you had a prior. So it's basically, in interpretation, is you have a prior belief on what theta could be. Maybe your prior belief is that theta is not between. Maybe in this Bernoulli case, it's not between 0 to 1, but it's actually between 0 to 0.5 or something. Maybe higher belief that it's between 0 to 0.5 rather than between 0.5 to 1. Okay. Then you can encode that here. That your belief is that maybe your p of theta is like between 0 to 1. In the example case, theta is just q. So maybe in the example case, I have a higher preference that it's theta is a continuous number. It's a random variable now. So maybe I have a higher preference, here on this side of the interval rather than the other side. Okay. This is a probability density function. It has sum up to 1. Integrate to 1. This you can substitute here. Okay. And so you have prior distribution on theta, prior belief on theta. You have here you have a likelihood, and this is the posterior probability of theta given the data that you observe. Okay. So, this is a likelihood for a generic random variable. So you can actually substitute this with the data. It's like the actual data that you get, something like this. Although there's log here, in the non-log version you can put it here, and then given the actual data, what is the posterior belief on theta? So here you will get another thing. Maybe in reality theta was somewhere over here. Your belief was that maybe the q value. Okay, let me not use theta. Just to be confused. So this q is a random variable, and I don't like using capital Q. Let's just stick with q as a random variable here. So let's say my prior belief was that q is distributed according to this way, but I observe coin flips, and coin flips, there are more heads than tails, which essentially is kind of indicating me in terms of the likelihood that there's probably q should be on the right hand side. So you'll probably observe a posterior with something like this. So you'll have a posterior distribution on q where there will be more mass on the right hand side because of your data part, likelihood part, that you observe more heads than tails. Okay. So this is just a Bayesian version of things where they don't want to condense it to any number. So here we are getting one number, maximum. This is the best estimate. There's a single unknown thing that I'm estimating. Here Bayesians don't want to kind of do that. They want to always have a distribution over everything. So here it's going to be a posterior distribution over our quantity of interest, which is q, after we observe some data. Okay, goodbye. Map estimation is a middle ground between Bayesian thinking and MLE thinking. Okay, and there they say, okay, let's think of a prior for q, but let's maximize the numerator. Okay, and that's it. Let's maximize over theta of probability of data given theta times probability of theta. So all they've done, MAP, is a middle ground where they're saying this is what you do anyway, this is the likelihood term. They're just adding on, multiplying with the prior. Okay. So this involves theta, this also involves theta. So it's kind of somehow balancing our prior belief and what we observe in the data. So I want to find the theta that best describes the data in terms of gives the highest probability mass, but also kind of balances out what our prior belief about theta was. Okay, that's called map estimation. Yeah.
So map's different from Bayesian because you drop the denominator?
No, the denominator anyway doesn't involve theta, right?
Okay.
So we drop it. We can still put a denominator or something, but then it's a constant. It doesn't depend on theta.
So how does map differ from
Bayesian? Yeah, here we are still estimating 1 theta. So we can put, let's say, remember argmax. So let's put this as theta hat, MAP, and here it will be there is a problem. Yeah, I mean, so maximize over theta. So this, let's call it theta hat MLE. So both are splitting out one number. I mean, so one number for the Bernoulli problem or a vector for, let's say, the other problem, like this problem. Right? And so now you can actually think of your ridge regression as, ridge regression has this additional term. It's like a prior. It's like a prior on a, I mean, there's an additive term, so you can think of, okay, in terms of probability, it was probably a product here. Okay, there were n products here, and there was one more product term here, right? And this product term is essentially this last guy. So this guy, because we had independent observations, there was a product of n terms here, right? And that we saw here leads to sum of n terms, and that's the sum of n terms here, same as respect to squares. This additional term is kind of interpretable as like a prior distribution that you're assuming over beta. Okay. Any questions? Took 1 hour for this. If you have any questions, I mean, this is not, I mean, so people have seen MLE. Any inconsistency with what I've said? Or can you kind of remember that you saw something else, or maybe saw the same thing? So ridge can be interpreted as certain prior on the theta or whatever beta in that case. Even lasso can be interpreted as a prior on beta in a similar interpretation like ridge. Okay. So what is that prior? The prior is going to be that beta is distributed with mean 0 and variance like identity. I mean, covariance matrix in identity. So that's related to your problem in your homework. Okay. And for lasso, this interpretation is basically something like there's some other distribution called Laplacian distribution. It doesn't matter. That leads to like a plus lambda times the absolute values of the coordinates of beta. Well, so in the sense that there is some way to explain why you're adding like some penalty type thing here, or even to explain why you're arbitrarily picking loss functions and minimizing them. They may correspond, with good chance, correspond to maximizing the likelihood according to a likelihood model that you kind of assume. Any other question? Any questions, Sam? Okay, so this is MLE. Actually, this is a relatively straightforward topic. So if you come across MLE in some very specific setting, all they are essentially the higher level objects are just some likelihood. They are defined according to some model, and they're just maximizing log likelihood. Typically, log likelihood they may also directly maximize without the log, but typically most people just take the log because it transforms products to sums. Okay, that's a very useful thing. So if there's a question in the exam, why a log? You can say it transforms products to sums. Products are hard to work with if needed. Yeah, so log of a times b is log of a plus b. Log of a plus log of b, right? So okay, I wanted to quickly cover Bootstrap. So let's take a break in 10 minutes. Is that fine? Because Bootstrap is not a difficult topic, but it's a topic which is very practical. So I'm gonna just explain Bootstrap procedure at least, and maybe. So Bootstrap. So that's it. MLE is basically just this, and I gave you an example. And so LDA is actually doing MLE, but we didn't really cover the MLE aspect of the problem. Okay? I directly gave you some formulas on what the estimates of the parameters could be. Bootstrap. So Bootstrap is So there are various interesting names given by by statisticians in the statisticians over the past several decades. There's something else called jackknife. There's Bootstrap. There's some other things, but so Bootstrap is something which is very useful. Even is very useful, especially when you don't have very simple models, like linear regression with this type of an assumption that epsilon is random. You don't have to do Bootstrap to get what is called a confidence interval of your prediction. So let's say you got a beta, right? You under this assumption, we said maximizing likelihood is the same as minimizing residual sum of squares. So we know precisely how to minimize residual sum of squares. We get a closed form formula for beta hat. Now you use a beta hat at any given new point x naught, right? That's going to be one prediction, one number. You can actually put a band around it and say that's one number that I'm estimating, but I can also give you a confidence interval of what where I can say the predicted value could be with high probability, right? So most of our regression models give you one number, one estimate. What is the prediction? Y, for any given new data point, what is y hat? Not y hat. Let's say x naught is a new test point, and you have a model. It will give you some y naught estimate. Y.
Can you draw like a picture of to understand what is the Bootstrap?
I'll get to Bootstrap. I'm not even explaining Bootstrap, right? I'm talking about confidence intervals. So,
yeah.
So you had a model. So x to y. You had a model f. Okay, maybe I should use here. X to y. You had a model f, right? F of x will give you a number, right? It hopefully approximates y. That was the whole premise from beginning. In this assumption, okay, because we are assuming there is a noise like this, right? There is a noise like this, which means that I can predict a y for any given new x naught. Let's only focus on this model. In this case, let's say there's a new data point x naught, right? I can pass it through my model. Let's say my model is some beta hat, which means that given x naught, my prediction is going to be equal to beta hat transpose x naught. That's my prediction, right? Now, but that's a prediction. But I know that y is a random variable, which is like which is Gaussian. So I'm predicting one number, but the actual in reality the y can be all over the place, right? In the sense, for some the true model beta, the true parameter beta, given x naught, I multiply this, I get a number. I add a random epsilon, so I get a realization of epsilon, and that's going to be the true yi that got realized. Or sorry, y naught that got realized. My prediction is just saying I got something estimated from data. I'm multiplying it with b x naught. I'm going to give one number, but the actual y naught was because I had beta, the ground truth model beta. I multiplied with x naught, and I added a realization of the this normally distributed random variable to get a y naught, right? X naught, y naught is formed that way in our assumption. So this prediction will probably never be equal to y naught, right? And so we're going to say, okay, since it's never going to be equal to y naught, can I say something about y naught belonging to an interval, which is going to be because I know that it's normally distributed, because I know that this is the type of randomness in this model. I can actually give an interval, maybe some y lower value, y upper value. I'm putting bars, underscore and upper score to just say there's some lower number and upper level. I can make this as the my prediction. I don't have to always predict a point estimate. This is called a point estimate. I can also predict an interval. Okay. In linear regression, you might have seen these are called confidence intervals. Okay. But let's not worry about confidence intervals. Is what the theme of this topic is. Let's directly estimate what are called. Okay. Bootstrap has a couple of purposes. So first purpose is Bootstrap for confidence bands. So confidence intervals was a term used for linear regression under that assumption. Let's not worry about assumptions because these types of assumptions are very too strong. Your data may not have such assumption. So Bootstrap is for any let's say prediction model, or actually any model estimate theta hat. It could be residual sum of squares beta hat, or it could be just maximum likelihood estimation q hat. Right? There were two examples there. For any model estimate, I can give a band around these estimates, or I can give a band around these estimates themselves, or I can give a band around the predictions of these estimates. In this case, there's no prediction here. In this case, I will use beta hat to transpose it with some new data point x naught. So this is a number. I can give a band around this number. So this is a number. This is a number. Don't worry about it. So we can give a band around these estimates. Okay. These are point estimates, right? Need not be just a linear model. It can be any model, and I can give a band around it. Is the objective clear? And any questions? Yeah.
In this particular interval, you are putting the minimum bar at y and the maximum bar at y bar. So y
No. So bars, don't worry about it. Okay. It's like y, some y1, y2. Okay. And yl and yu. Some two numbers that you can. So what I'm saying is for linear regression under that model, there are. I haven't shown you how yl and yu are computed, but it's some very standard thing. I don't want to go into that detail. But you can report these two numbers and say the true thing belongs to this interval, okay, with probability 90%. Remember, plus standard error, plus or minus 1.96 standard error or something like that. Those are basically what this gets. But people who don't know, don't worry about it. All I'm saying is, for a very specific model, there is a very nice way to get these two numbers instead of one point estimate. Okay, but that was a very stylized specific model, and I'm saying I'm going to give you similar numbers for any model. Okay. It need not be even a supervised learning task. It can be even a model like estimating parameters using MLE. Right? Q hat was just an MLE parameter. It's not related to supervised learning. Right? Is there any other question? Yeah.
So let's say for a linear model, beta transpose x naught it's a point.
Yeah.
And the estimation of theta will give a range around.
This is a vector. Theta, if you remember that the residual sum of squares equivalent was that normal distribution assumption and all that. So beta is a vector. This is a point estimate of estimated prediction.
So in Bootstrap you will get the range around that point estimate.
Yeah, range around this point estimate. Yes.
So how different is
so this can be almost the same as this if those assumptions hold, but you don't want to make you want to get still bands or some sort of uncertainty ranges, even if you don't assume things like normality and so on. So because of normality, there is some closed form. There's some nice way of computing these two, but we are going to talk about very generic way of computing some range like this, and I'm calling that range confidence band. In the linear regression case, called I think confidence interval. Any other question? I wanted to take a break, but now I haven't even told the procedure. So 10:45. Because it's a very intuitive method, and the method is just I'm going to describe the procedure. It's like it's a procedure similar to k-fold cross-validation, but don't confuse with k-fold cross-validation at all. Like ignore k-fold cross-validation, but it's going to be a procedure. It's going to have few steps, 1, 2, 3, and let's look at those steps. Step 1 is going to be so since I'm talking about any model, so let's say Z is my Z matrix, okay, how do I represent Z matrix? Okay, I don't really need Z matrix. So let's say Z is all my data points Z1 to Zn. Just concatenated. I know it's basically a list of my data points, and I put a bar here just to say that it's not a random variable. It's it's just a collection of data. Okay. Step 1: create for little b is equal to 1 to b. So this is going to be a parameter, capital B. So I'm saying do a for loop for each little b. I'm going to create some other data which I'm going to call Z star b, which is just going to be sample n observations with replacement from Z. Okay, that's step 1. I'm just saying, basically I'm saying create D data sets where each of these, I created these data sets. I was only given the original data set Z. These data sets I'm going to create by just saying, okay, I have n observations. Let me pick the first, to create this data set, maybe I want to create this data set in this instance. I want to create the data set with the same number of observations, n observations. So I'm going to sample the first observation from the original data set, one of these guys, and that will be my first row. Yeah.
When you're only doing n observations, though, doesn't that take all the data?
No, there's randomness, right? Because I'm sampling, maybe I sample the first guy, to get the first row. Maybe I got Z1. In the second row, maybe again, by luck, because I'm sampling is actually when they say sample with replacement, sample uniformly with replacement. In a sense, yeah, you may get again Z1 or something. So you create B such data copies. Okay. You create these Z copies. Step 2: create models. Create models. F star B. I'm just using F star B. Like this F is like, let's say something, a model, like a linear regression model or LD, sorry, not LD, ridge regression model or something else. Okay, we've only seen linear models, but think of any supervised model here. And once you've created the model, so that's it. Those are the 2 steps for doing something. So instead of creating one model, I have to create capital B number of models. Now to get a band, a confidence band, let me, somebody gives me x0. Given x0, I'm going to find f star b of x0. Let's say f star 1 of x0, all the way to f star capital B of x0. Okay. And maybe I should put a hat because it's things which use the data and create in the model. And so I have, instead of one prediction, I have B predictions. Okay. And what I'm going to do is just sort them. Sort the B numbers above. Okay. So maybe the numbers are, like example, let's say the numbers are 10, 7, 8.1, 4.3, 5.7. So just sort them. Maybe it's 4.3, 5.7, 7, 8.1, and 10. This is sorted order, right? And then your band would be just something like picking the third number from the left and third number from the right. Okay? Or maybe not third here. Let's say the second number from the left and second number from the right. So your band would be 5.7, 8.1. That's it. And if you want a point estimate, just average and you get some number. That's your point estimate. But point estimates, if you are gonna just report point estimates, you don't even care about this. So get a band. So these are actually the technical term here is what are called quantiles, I guess, or percentiles. Basically, something like the second number here is essentially like the second number specifically, I don't know. So let's say there are 100 numbers, and you're picking the fifth number from the right and the fifth number from the left. Then it's something like 90% confidence band. In the sense of you're picking the fifth percentile and the fifth percentile. Okay. The fifth percentile and 95th percentile. Okay. Those are called percentiles. Just a word, but that's the implementation. All I'm saying is create copies like this. This is important, and sort the estimates and get the bands by shrinking your you have a list of numbers. Just shrink it on the left side and right side. That's it. That's Bootstrap procedure for getting confidence bands. Any questions? I mean here, okay, in a sense, it's not the Bootstrap procedure. There's so many variants proposed by lots of people. This is the most vanilla version because for example, why choose exactly n observations here? Why should I do sampling with replacement, right? Why should I cut off? What is the exact number to be cut off here? Like, should I take the second number from this side and second number from this side, or third number from this side and third number from that side? There's so many choices, right? But this is like in spite of model all those choices, this is a way to come up with confidence bands, uncertainty intervals around your point estimator, point predictions.
So, is it for any given model? Is it a way to estimate our model with some?
If somebody asks you, so typically people don't want to just know a single number. They want to know what is your uncertainty. Like you are estimating that the revenue next year is going to be 5 million. Is it 5 million plus or minus 5 million, or is it plus or minus 500,000?
Nice.
So yeah.
Does this have any relation to mathematical variance, or?
Yeah, it has. I mean, we are kind of completely sidestepping the theoretical properties here because there's a lot of randomness happening here. So we can look at expectations and variances of these things because I'm doing some randomness inside. So and you're asking if there's an interpretation related to variance with this guy. There is actually. So I mean, in the sense, in the special case of linear regression, clearly this is precisely related to variance, right? This YL, so YL is actually whatever is the prediction minus, let's say, 1.96 times sigma. So sigma, let's say, the variance is the same sigma here, and y up is like plus 1.96 times sigma, where 1.96 just comes from if I want a 95% band or something. I mean, yeah, some interpretation there.
Is it often with this band?
Here there is no, because these models can be arbitrary, right? So we'll see some nonlinear models, nonlinear regression models in the subsequent lecture. So there it's really no, it's a very constructive procedure of constructing hats, and so there's no very nice interpretation like something like this for linear regression, linear models. So there the band is just it's related to variance, but not. It's probably difficult to quantify.
Does this method often yield the rigorous confidence intervals for what you're
Yeah, so this is what you should do. Whether this gives the same as that, I'm not sure. In the sense, yeah, whether if you report this, people report this. Like in research papers, when people report uncertainties around like plots, unless they have specifically assumed some linearity and so on, people report this.
I guess kind of related to that is the value of big B. Is there some optimal value for that? Because I would think an optimal value would be one that they
Yeah, potentially. I on the top of my head, I don't really recall the relation between D, that interval, and this interval. I mean that interval and that interval. I don't know. So that's Bootstrap. What's that? Okay, let's take a break, and let's take a break for. Depends on how much you want to review. Let's take a break for 7 to 8 minutes. And if you have questions in between that are really like confusing you fully for the in terms of the first 6 lectures, you should definitely kind of make use of time after the lecture or even now.
Posterior is
this is just the names given to this conditional distribution. This is called likelihood. This is the name given. This guy is called the prior, and this guy is called the posterior.
so this is the probability of your model given Z.
Yeah. So now
And
these Bayesian guys interpret the model parameters also as random variables. That's something that we have seen for the first time in this whole course, and we will not generally use this type of knowledge. I just wanted to kind of say that since Bayesians, for them nothing is fixed unknown, everything is random. So they'll have prior belief on what the parameter should be. They got the data, and they'll have a posterior belief of what the parameter should be, and that's just related to the Bayesian. It's just a Bayesian.
You said the prior is distributed with mean 0.
Oh, in range regression, like to interpret this term, I'm just saying that this term is like Bayesians believe that the betas are mean 0 with variance, something related to identity. I mean, this is a problem that you had in your assignment. Yeah. So whatever the lambda, there was a tau there. So this variance I don't remember. Yeah, but they consider this betas to be normally distributed with mean 0.
And I think after class I'll also ask about that.
Okay. I have a snapshot of my. So last time I
know last week some people asked you questions about that.
Oh, but they didn't share the snapshot of the thing?
They did. But,
oh, they did? Okay.
Yeah, like they showed me like what you showed on the board, but I don't completely understand.
Oh, okay. Okay. Oh, you have this.
Yeah, I can just ask you after class.
Okay, you have this. I doesn't rotate, but you have this board, right? I wrote some steps. Yeah. Okay.
I'll ask you after class.
Okay, so let's resume. Sorry, it was a short break. So I just want to kind of wrap up Bootstrap. So here we said we can make a prediction model for every Bootstrap sample. So this is called a Bootstrap sample. Okay, Z star B is called a Bootstrap sample. So sample is, I guess, in statistics, sample is like a collection of observations. So that's why I don't want to, and sample is also overlaid here. Sample means to get something from a bunch of things. So that's why I use observations or examples mostly for the individual realizations. Right? This is called a Bootstrap sample. And the point I wanted to make was that the Bootstrap sampling is, Bootstrap based confidence bands are also valid for, can also make sense for MLE estimation. Right? In MLE estimation, which I erased, you could get a theta hat, like a Q hat, right? You got the Q hat because you use the data. And now you have B different data samples. You can, for each sample, you can get a theta hat, a different Q hat. Right? So I'm just saying that you can solve capital B number of MLE problems where the data for each MLE problem is Z star B. Right? And, I had original data, I have B new data sets. It's like new data sets. And so for each data set I can solve an MLE problem. That will give me different numbers. And then again I can do the interval like this. So that anyway is part of this. And the second use of Bootstrap is also to get an estimate. So, but this is not a very favorite method, or at least personally I don't favor it. I have never used it. But you can also estimate generalization error. So this should ring a bell. Estimating generalization error is what cross-validation does. Estimating generalization error is what even AIC and BIC do, but then they just take the in-sample error and just add a bonus. Remember, there was like a bonus, some additive term they just add and try to, but the whole reason, or at least we didn't look at all the derivation of how such an additive term comes, but the intuition there was to add such a term so that the added term plus the in-sample error is somewhat estimating generalization error. Okay. Even with Bootstrap, you can estimate generalization error, and it's going to be it's a complicated formula, but it's not too complex. It's just to write. Okay, it's going to be for each data point xi. Yi. Okay. Find C minus I. Okay. What is C minus I? This is a notation. Okay. This is not C to the power minus I, but C is a number. This C minus I is gonna be all those little b's where xi yi was not part of the data set. Is that clear? Because sometimes, maybe xi yi is, let's say, this guy, somewhere, ith guy. Maybe in some sample it never came up. Because you're sampling with replacement, you never sampled the ith guy in some sample. Ci is just those indices of B where you did not use ith sample as an ith observation. And the intuition is basically very similar to cross-validation. Basically, I'm trying to figure out where did I not use xi yi, okay? Which models, I'm creating, capital B models. There are some models which did not use xi yi, right? So for those models, I can use xi yi as some sort of a validation data points. That's the key intuition. Yeah. And so for those samples that where you've not used this observation, you just take the average of the loss. So maybe there are 3 indices. Let's say maybe for B is equal to 1, 2, and 3, you never used xi yi because it never came in the sample. Maybe for the rest of the guys it came up. Then C would be just 1, 2, and 3. Okay, C minus I is just saying where it was not, I was not present. It's just a kind of shorthand so that you understand, okay, C of minus I is just saying pick these little b's where it was not used, I was not, didn't come up, and then you just take the maybe there are 3 of them in my running example. You just take the average over the b's, okay, which belong to C minus I. So this notation I think I've probably used multiple times. This is just belongs to. So I'm just saying what are the b's where which are in the C minus I, and for those b's you had created a model f star of b. For those b's you had created a model f star of b. You can just use the loss function of that f star of b, b of that xi, comma yi. I mean, there is a loss function that you use to build the model, right? It's just saying these xi yi happen to be out of sample observations for these models, so just average them. Okay. And then average these type of numbers for all the i's go to 1 to n observations. That's your estimate for generalization. Is that a good estimate, bad estimate? There's a lot of mathematical derivations the statisticians have done, but we'll just understand the procedure for this case. Let's not worry about whether it's a good or bad. I mean, it probably is a bad estimate unless properly chosen, B and all that. But this is an estimate of generalization.
Why are we taking an absolute of C minus I?
Oh, it's just a count. I mean, as I see the set, so I'm just saying what is the size of the. Yeah, basically it's the number of terms that I'm summing here. It's like average.
I'm just curious, what are some better methods for estimating generalization?
Oh, cross validation. That's we saw in the second lecture itself, or third lecture. Yeah, cross validation. So methods to estimate generalization are cross validation, AIC, DIC, Bootstrap. But I would prefer cross validation because it kind of makes minimal assumptions about the problem setting. Here, I mean, the thing is, cross validation just I think probably has the fold size. The fold as the only thing that you can kind of tweak pretty much. Here there are so many things, right? Like B, why is it N here? That could be something else. And also this estimate may be different based on which models you are looking at. In the sense of this estimate may be a bad estimate or good estimate depending on which supervised learning task you're looking at. That's something like basically ultimately you want to have a procedure which is like not too dependent, it's quite robust to whichever method you're using previous, in the previous part of the work. These are not quite robust is what my impression is. So I would prefer cross validation. Any other questions? Okay, if not, then let's do a quick review. So do you feel strongly about any particular topic? Okay, there is probably a list of topics somewhere. I don't know. Okay. So, there are several topics. Linear models, k nearest neighbors, comparison between k nearest neighbor and linear models. I'm just reading out what's written in the notes. We'll discuss some things in more detail soon. Statistical decision theory is just what is statistical decision? Is it the EP stuff? Yeah. Okay. And then curse of dimensionality, which is basically like wide, I think I kind of repeated it quite a few times in that lecture. That if you had really small data, if there was no curse of dimensionality, k nearest neighbor is almost the best thing for both regression and classification. Okay, It's just that in high dimensions, the notion of neighborhood kind of fails, because for the same amount of volume per coordinate, we kind of saw that you pretty much have to go all the way to age 0 to age 99 just to get that volume in very high dimensions. So that's a manifestation of curse of dimensionality. And curse of dimensionality is a loose term that people use for many different settings. You might have seen curse of dimensionality. Have you seen curse of dimensionality anywhere else? No. I mean, anything where you're saying computation is hard because dimension has increased. Estimation is hard because dimension has increased. Things like that. People use the phrase loosely. And then supervised learning. Probably watching sports, maybe. Linear regression. Bias variance trade-off we saw for KNN. We saw that the EPE, squared prediction error, can be broken down into a couple of terms, and there were 3 terms, but the key term was a bias squared term and a variance term of the estimator. And we just try to interpret what does bias mean and variance mean for K nearest neighbor, because that has just a K parameter. So K influences what does it mean, what does it mean to be the model to be biased versus what does it mean to be for the model to be have high variance. Okay, we did that. Subset selection, ridge and lasso, I would consider them as a family of things to further bias linear models. Okay, in fact, the first 6 lectures are all about linear models, so you don't even have to worry about other fancy things like random forest and all that stuff. We'll get to that later. So as I said, ridge, lasso, and subset selection are further biasing your linear models, especially in the case where you have too many input variables, like some of them may be irrelevant and so on. Then these are good strategies to get rid of them, essentially, or minimize their impact on your model building, right? And then we looked at classification in last lecture, where we said, you can actually just use linear regression for classification by just doing 1-hot encoding of the output variable. Instead of capital G, we can map it to k-dimensional capital Y, where each coordinate is going to capture whether the G was taking a label little g or something, little k or something. But then we said, by an example, we said, it looks like it fails for a very specific data set, and that is called class masking. So we illustrated that for a specific data set, but we don't know in higher dimensions, whether class masking is actually happening or not. Okay, and so we said, okay, let's not prefer linear regression, although we can use linear regression for classification. Let's now look at some more methods, but the key characteristic of those more methods, which include LDA and logistic regression, is that you have linear decision boundaries. Okay, so that's why they are in the bucket of linear models. They are linear decision boundaries. And we also looked at one tangent there, which was QDA. QDA had quadratic decision boundaries. Okay, so those were the regression and classification models that we've looked at. And then we also looked at model selection very briefly. But model selection, we've already covered the major piece, which is cross-validation. So the other techniques are not in vogue, I think, these days. So that's why I kind of didn't pay much attention to them, AIC, BIC, and so on. And today I talked about MLE. Many of the linear models. So although I didn't spend much time on, so the linear model that we saw, LDA, erased it. LDA is actually can be thought of as an instance of maximum likelihood estimation, right? Because I'm completely specifying the joint distribution between data. How does X realize given class is exactly normally distributed? There is a class specific probability, that the data can be that pi. Remember, pi was a probability that pi j was a probability that observation I belongs to observation I belongs to class j, right? So MLE is important, and it's unifying. And in regression side, we looked at ridge regression, and it's a part of your assignment as well as assignment 2's first question is kind of beating around this concept that MLE or maximum a priori estimation is gives you essentially the ridge penalty, the second term that you had, like sum of beta j squares, right? And then the last part we looked at is Bootstrap. It's a way to think of, we don't have to always estimate point estimates in regression problems. You can get intervals like this. For classification, it's not going to be intervals, right? Classification, there's no ordinal relationship between any of the classes. So there, something like this is not there, but yeah, I mean, they really don't know. Like, if this is not the class, which other class would it be? You can probably give a second class or third class as an estimate. Because if you remember, the classification model was, I mean, not model, but any model of, your class prediction is going to be max over L is equal to 1 to, let's say, capital K classes of R max is going to be your prediction, right? G hat of x is, the probability of G is equal to L given x is equal to x, right? So this was the actual, this is the base optimal classifier. Like, if you knew exactly the joint distribution, you would know this conditional distribution, and this will be estimated at any given point x. Okay. So an equivalent of Bootstrap would be, not just take the max. What is the second max? What is the third max? We just sort these probabilities. These are L numbers, and maybe the best class may be dog, maybe second best, maybe if it's not a dog, it's a cat, and so on.
So based on the probability.
Yeah, you just sort them and look at the. That's what people do. People do in practice. But there's no Bootstrap equivalent thing, as far as I know, unless you can correct me. Yeah, and once you restrict to models, I mean, there's, and the whole point was, LDA would be some parametric model which approximates this true thing which I don't know. So the parameters were the LDA specific parameters, and same thing with logistic regression, right? There is some parameters. In a sense, you solve a logistic regression problem, it's going to give you something like this, right? Where it's actually equal to e to the power beta L transpose x divided by sum of e to the power beta, I guess, j transpose x. I think there was something else. J is equal to 1 to t. Sorry, j is equal to 1 to k minus 1. I guess plus 1. I don't remember exactly what the formula was. Something like this. So that's what I mean. So parameter just means these betas. Beta, which are k minus 1, such betas, which are p dimensional. Okay. For logic regression. So. And this is multi-class logic regression. So we are really looking at general versions, and we are not specific to two-class stuff. Anyway, so okay. So now it's actually, so is any of the topics like difficult to parse in the lecture notes? Don't worry too much about going through ESL book, in gory detail. It's not very necessary. You can if you want to. If you want to really ace the test plus get 2 extra points, then yeah. Any topic that you felt was difficult, because I don't want to. If I start covering from the starting, I'll miss some topics at the end. if given the limited time.
I just have a question on KNN. So with KNN, there's more variance and less bias, right?
KNN has more variance when k is really low. When k is 1, smallest value that you can pick, you have very high variance, which means the bias is low.
As k increases, the bias
increases. Yeah. Biasing just means I'm not tying myself too much to, like I'm increasing my neighborhood, essentially. I increase k. So when I'm increasing my neighborhood, I'm taking a huge average. It's like smoothing. Biasing is like smoothing things, right? It's like I average out things, so even if there is some, I guess outliers in my data, I can smooth them out, something like that. Interpretation.
So the interpretation isn't that your results are somehow.
For large K, yeah. So think of the extreme case when K is n. You will predict constant every time. Okay, that's like the smoothest thing you can predict. Some constant. In fact, that constant would be just y bar, average of all my realizations of output variables, right?
That doesn't mean that your results are not as valid.
If the underground, if the ground truth is actually constant, then that's the best case, I think. But you don't know. Right?
So just to go on that, when you're saying A equals N, it has a low variance because you gain one answer.
Yeah, you want to answer all the time.
Bias because you're only gaining
Yeah.
one answer.
Yeah. So high bias because almost no variance. So what's your question specifically? Because it's a
I think they're right.
okay. So I think we studied this, right? When K was low, we actually derived it by looking at the bias variance trade-off and specifically substituting KNN model there, and we saw the inverse dependence of variance on K. Yeah, inverse dependence of variance on K, and somewhat linear dependence of bias on K. Bias squared on K, something like that. Is there any topic which was difficult? I know some topics were difficult, but I don't know which topics are difficult for you guys. Huh?
Can you quickly go through very quickly through LD and QDA?
Okay, I will do that. You have a question? Greater than 2 predictors. What does predictors mean? Oh, in the input variables. So I don't think in my discussion did I pin it to two dimensions? Never, right? 2 dimensions. Okay. Okay. So LD and QDA. So let's look at that. Any other? Yeah.
I wouldn't mind looking at the E and the bias variance.
Okay. Okay, so let's quickly look at LDA and QDA because actually, where is the structure side? Yeah, so specifically, I know, so you had a more specific question of what does it mean in 3 dimensions? What does LDA kind of look like in terms of the decision boundaries? So decision boundaries are always the same, right? So in fact, as a consequence of our assumptions, the assumption was that the probability of, in fact I wrote somewhere, okay, probability of x equal to x given g is equal to L was normally distributed with mean L and common covariance term. And we said the probability of, it turns out, okay, in the sense of you can compute this, probability of g is equal to L given x is equal to x divided by probability of g is equal to, last time somebody got confused when I used k, L, m, let's say m, oh m is used somewhere else, I don't know, okay, x. So this is saying it turns out that for any 2 classes, the probability of, this is the class condition, this is the probability for given x, what is the probability that it is in L and what is the probability is in M. This log probability happens to be some, constant plus x transpose some other constant, not constant, but let me just put some numbers. Okay, there are numbers which depend on our model, like mu's and sigmas. But ultimately, you get something like this. It turns out, when I say it turns out, I know this. Let me assume that the probability of g is equal to L is actually equal to pi L, I think. So this pretty much says what the parameters are, right? There's pi L, mu L, and sigma. There are 3 parameters. I mean, in the sense of two parameters per class. There are k classes and so on. But anyway, these are the parameters. And first, you need to identify that this is a complete description of a joint distribution between x and g. Why is that? Because a joint distribution between x and g, x is equal to x, comma g is equal to L, is actually equal to probability of x is equal to x, u and g is equal to L, and the probability of g is equal to L. Right? You agree with that? This is just any joint distribution can be broken down into parts like this. I mean, not just like this, you can also flip it. Probability of g is equal to L given x is equal to x times probability of x equal to x. Right? And with those two, you can actually get the base rule. Right? So I have completely specified the joint distribution. It has these parameters. When I say it turns out, you actually can compute this guy. Assuming these two, I know the joint distribution. You can just plug these guys here. I can also find the probability of g is equal to L given x is equal to little x. Using, for example, the base rule. Then you will see that this ratio is actually equal to a linear function like this. Why is it a linear function? Crucially, it's because there's a sigma. The same sigma appears in both the numerator guy and the denominator guy. Okay. And now coming to decision boundaries. Okay. Decision boundary is basically some part of the input space, some part of this input space, x space, where you are not sure, given your model, you're not sure whether you want to kind of, let's say pick a point x, you're not sure whether which class it falls into. There's so many classes, there are k classes. Let's not worry about all k classes all the time, together. Let's pick any two classes, for a given point x. Is that the probability that a class, probability that it falls into L class and probability that it falls into M class is the same. If it is the same, I'm not sure which class I should classify this point as. So that's a decision boundary. So for every pair of classes, I can find the decision boundaries, and they happen to be linear. Why is that? They happen to be linear because this is pretty much the decision boundary, right? If this was greater than this, then this will not be. It's linear because if these numbers are the same, then log 1 is 0. So this is pretty much giving you the decision boundary is characterized by this number equal to this number, and if this number is equal to this number, this is true. Okay. So for x's for which this numerator is equal to this denominator, for the same x's, this is equal to 0. Okay. So the decision boundary is linear. In the sense, if this is 0, then numerator is equal to denominator, therefore it's a decision boundary. X is on the decision boundary. Is that clear? So you can go in 3 dimensions and try to visualize. If you visualize in 3 dimensions, think of like 3 blobs of points maybe, and then you have like planes between these 3 blobs. Those planes will be. This is the equation for a plane in 3 dimensions or more. If you really want to visualize, like maybe there's a huge class here, there's a small class here, and another small class here. There'll be like planes between them. Okay, and when you are thinking of planes, don't think of how they all look together. Just pick 2 classes and just there's a plane cutting them. Okay, they were not thinking about other classes at the same time.
Like in the last hard book, it's talking about the same sort of thing. So as long as the covariance is the same for all classes,
yes,
it's always going to be, assuming that assumption holds,
yeah,
it's always going to be a linear.
Yes, it's very important actually. That's a big difference with QDA. Because we are assuming the same covariance matrix for any class, whether x is normally distributed because it's in class L or because it's in class M. They all they may have different means, but they have the same covariance. So we are assuming they are same Gaussians, just the means have changed. Okay. Because that's true, this thing is linear, and you can check that is because a quadratic term in x. So nominally distributed just means there's going to be there's going to be a e to the power something minus x minus mu L transpose sigma inverse. Okay, that's why I didn't want to use sigma, somebody got confused. Let's call this, let's say for just this discussion, let's call it B, so that you don't confuse it with summation. So B of x minus mu L, right? So something like this would be the exponent of your Gaussian definition, right? If you take the log of A by B is log of A minus log of B, right? If you take the, it turns out that this term is also, essentially an exponential. I mean, you can just see that, right? Let me just, P of G is equal to L given x is equal to x is actually proportional to P of x is equal to x given G is equal to G is equal to L times probability of G is equal to L. I will put a proportional sign, let's actually tell it equal to probability of x. This is just base rule or the definition. Now, this doesn't depend on L, so if I divide two numbers with the same denominator, I'm just ignoring the denominator, and you can see that this guy I assume normal, which means that there is an exponent like this, e to the power something like this, right? There's a coefficient here, maybe C3, 1 by square root 2 pi, some determinant of sigma or something like that. Don't worry about the coefficient. Sorry, determinant of D. So if you take the log of A by B, you're taking the log of A minus log of B. Log of A, forget about this constant, there's an e to the power minus something. So log of A would be just this term in the, this e cancels out, right? So you just have this, and this guy, if you just look at it, there's going to be a product of x and an x. Like this, there's a square here, there's a square, there's two terms here, there's two terms here, so you'll have four terms, right? If you expand this out, there's a, x times b inverse, x transpose b inverse x, minus mu L transpose b inverse x, and so on. There will be four terms. There will be one term which will involve x transpose b inverse x, okay? For the denominator guy also, there will be a x transpose b inverse x. Because the b is the same, you just cancel it out. And that's why it's linear. For QDA, this is not B but BL. Okay? And so you can't cancel that out. And so your decision boundary is quadratic. Okay, it's going to be like curve. So LDA versus QDA clear? For those who, I guess, study.
How did you transfer from like LDA to QDA?
QDA is when I said subscript, it's not B common for everybody. There's a B per class L, which means that you can't cancel the quadratic term x transpose B L inverse x.
Because we have more than two.
No, QDA is just a modeling choice. I'm saying instead of normal with the same covariance for every class, I'm saying there's a different covariance for every class. That will give you a quadratic term there. Okay, I mean whatever, two quadratic terms. One, they don't cancel. The decision boundary should be quadratic. So there's a discriminant function. This is, discriminant function is going to be related to just the log of the numerator. Essentially, the discriminant functions that we define, remember, is just a log of the numerator, because denominator doesn't depend on class anyway. It's the same for every fixed x denominator is just denominator, so we don't care about it. It's like an offset. So discriminant function for LD and QD are just a log of the numerator. So there will be a log of pi L, one term, and then the log of this guy, but this guy is just a normally distributed thing, so you just expand it out. Log of something normally distributed, you just focus on the exponent. There will be but this CC cam will also have a B, just don't ignore that, but that's not a big thing, it's a minor thing. Okay, should we get into bias variance? it's almost the same. So statistical relation theory, there's not much going on. It's basically the observation that expectation with respect to xy. So in statistical relation theory, we were not thinking of any models at all. So for any fixed, so for any model, sorry, we were not thinking of data derived models. We were not thinking of hats. We were saying, okay, let's say there's a model which maps from x to y. So this is actually I don't know if I'm using this notation. It's just this is something which people use to kind of say a function. It's a map from x to y. Okay, this is a notation we use, but let's not worry about it. For any model, it's not data derived. Let's say for any model, I just want to know what is the expectation of y minus f of x squared. This was the expected square prediction error. Expectation over x and y, which are random variables, right? And we said, okay, for any model, this is true. So what would be the best model? Okay, I mean, so now it's not data related. I'm just saying I have a joint distribution between x and y. That's why I have subscripted p. E with x and y. I could have also written p of x, y here. Just say that expectation with respect to this joint distribution of something, and you can tell me, I know this joint distribution. Let's say, what is the best f that I should pick? So basically something like minimize this over all functions, all maps. Okay. And this problem's solution. So let me not, if needed, I'll derive. But the solution for this problem was f is equal to whatever f. Let's say the solution is f star. F star of x was equal to expectation of y given x is equal to x. Okay. What is this explicitly? This is actually just the integration. Okay, let's not worry about. Yeah, that's integration of y of p of y is equal to y given x is equal to x d of whatever range of y is. This is the definition of this. Conditional expectation just means, it explicitly says something, then just think of that as the conditional probability in your expectation. So expectation of y is just whatever is the thing in there is whatever is over here is the same thing here, realization. Summing over all realizations over which probability? This is conditional probability. So this is the best solution for this objective, is what we showed in the statistical relation theory section. Is this clear? That this is what we came? And in fact, after this, we went on to say KNN approximates this, and linear regression approximates this, and so on. Right. Now the question is, why is this the best solution? Is that what you want to understand? We can derive. We can just take the calculus, take the derivative and see that is the solution. Do you want to do that? No. Yeah, it's actually okay. So it can be wrapped up in a few minutes. Let's say less than 5 minutes. So we have more time for other things. So the key observation was that we are searching for a function, right? What is a function? The mental picture, intuition picture is that function is just a table. It's basically a table that says, okay, it's a table where it says x and f of y, f of x. For every x value, I want to know what the f of x value is, right? Although it's a very high dimension table. If it's a continuous function, it's like too many x's. For every x, you want to understand what y is. But because it's a table, in the table view, minimizing our function is essentially saying find the best f of x value here, find the f of x value here, find the best f of x value here. So it's actually just several numbers that I need to set. Happens to be infinity or whatever, doesn't matter. But I just need to set all these numbers. If I can set all these numbers, that defines my function. Right? So it turns out that setting all these numbers can be you don't have to think of setting all these numbers together at the same time. You can just focus on one row of this. Okay. Can I set the best number for just some little x? Right. If I can set a best number for any x, little x, then I know what's the best number for. Then I know the rest of the guys. If I solve the general problem, it says like for a given x, what is the best number that I can set here? Then for every x, I know what's the best number I can set here. And the claim is that the best number that you can set for any given x is precisely this. Right. And there's a couple of lines in the notes which just says why should we, we are trying to find best numbers for every x together here in this problem. Why should this be the same as finding a best number for one x? Because this problem is simpler, like considerably potentially simpler. That I just need to find one value here for a fixed x. What's the best f of x that I should take? This problem is saying for every x, what is the best value I should take? Because I'm trying to optimize for the whole function, whole table. And the two lines in the notes are saying, okay, why this problem is the same as this problem. And it's the same because each problem, because your choice of f of the number here has nothing to do with what number you choose at the subsequent points or any other place. That's the intuition. That what I choose here, let's say I call it z, that has nothing to do with what I choose right next to each other, right? A point above it, a point below it, or some other place. Okay. That's the key observation. Because this is, or in other words, all I'm saying is, I want to minimize the square error in this particular case. The f of x that I choose for some little x that closely approximates y has nothing to do with some other f of x that I choose for some other y at some other place. That's unrelated. And so I can focus on just the problem for a given x, and that's why there's a given x here. This given x here. Is that clear? And in terms of like derivation, we said okay, this expectation is actually expectation with respect to x of expectation with respect to y given x of this thing y minus f of x squared given x, something like this. We wrote this is just why is there two expectations now? There was only one expectation here because joint distribution can be factorized as a conditional times so this times p of x, right? So that's why this expectation is with respect to p of x, this expectation is with respect to y given x. It's something that you can write out. I don't think there's much intuition here. So and then in terms of derivation, we said okay, let's just focus on this problem. This is basically the intuition that setting a value here has nothing to do with setting values anywhere else. Okay. And this problem, the optimal solution happens to be this solution we just said is okay. I don't like to use integration. Let me just use summation here. Just for I don't like integration. Okay, so summation of what is this term? This is just summation of y minus f of x is fixed some little x. Okay, let me not use f of x. I just want to fix x. Let's say f of x is some z. Okay, I'm just using variable z instead of x. F of x because this is the number I want to figure out. Right? So y minus z squared. Its expectation. So pre of y is equal to y given x is equal to x. Yeah, this is the expectation. So this is summation over y or integration over y dy if you add. This is the same as this internal thing. Do you agree? The expectation of something, and that's something I just wrote here. Okay, x is fixed, so this number is anyway some fixed number that I need to figure out. And the only other thing is this guy. And this I said, okay, how do you minimize this over z? Yeah, if you minimize this over z, you will get this. Okay, let me actually use the integration, doesn't matter. Okay, so the only thing, when you see integration sign, you might get confused, but don't worry about it. Just think of minimizing z as just taking the derivative of this guy inside, okay, and setting it to 0. And setting the derivative inside equal to 0 will give you a term which will ignore this. And z will be equal to this. Taking d by dz of this thing will imply that z is equal to integration of y, d of y is equal to y, even x is equal to x, dy. Okay.
Basically, over here we are approximating best z, which minimizes our RSS for a given y given x, right?
Yeah, so it's not an RSS anymore. Yeah, it's not empirical anymore. There's nothing here is empirical. It's saying given a true distribution, this is called a regression function. I think we defined it. Yeah. But it's like a squared error. So statistical relation theory done. What's the next one?
So you integrated, but
Yeah. So that's why I said I don't make an integration sign. You can take the derivative, switch it, which is not always correct in mathematics. But here, let's just do that sleight of hand and go ahead. No, you may want to know what is regression function, why, for example, like you probably want to know this, that this is a solution, but you don't need to derive this. Don't do anything like this. Probably, huh? No, this is not. I'm not going to ask you to take the derivative of this and tell me, like, because first of all we are doing a lot of, we are doing it sleight of hand, several places. So, but it's an important concept to kind of understand, things in the first lecture. In the first lecture, we were just saying, oh, there's this k-nearest neighbor method, there's this linear regression residual sum of squares based method, without any statistical backing. Here, there is some, this lecture is talking about there is statistical backing for what KNN is doing. It's basically approximating this. You need to understand why and how it's approximating this. Okay. And you need to understand why linear models are approximating this, or how they are approximating this, and what are the shortcomings of the approximations. Those will be the questions. And similar in pattern to the questions you see in the notes. I think in the notes maybe there's a variation of question like why, what is the shortcoming of linear model approximating this? Such a question probably is there. Okay, statistical relation theory done. What's the next? Bias variance trade-off. The thing is, you don't want to. So the thing is, in terms of time, you don't want to spend time of me showing the derivation when it's not really useful, right? It's not potentially going to be useful. If you really want to just get understanding of it, yeah, I can go through it.
I think someone else asked a question. With the various models, they all have assumptions. They all have this shortcoming.
Yes.
The bias variance trade-off.
Yeah, those are what you need to know. Not the bias variance trade-off, not the last part, but what are the assumptions? What are the shortcomings? Is there too many parameters? Is there a closed form expression? What is the, for example, ridge regression? What is the high lambda mean? What is the low lambda mean? Like the coefficient here.
Well, we have all that in notes, but it'd be useful for to get a summary of that.
Those are too many questions. Cannot be covered in 15 minutes. I think people have attended the class. I think most of you have attended the class. Would have heard these comments, right? When lambda is low, what does it mean? When lambda is really low, it's basically the original regression. We are not really doing any ridge aspect. If lambda is very high, then we are already saying there's a fixed, very small budget for what values of beta you can set. You cannot really, set a huge bias.
can we once go through everything like in terms of the penalty?
Penalty. Okay, I can arrange this Bootstrap stuff, right? I don't think I wrote anything else. So, ridge was basically y minus x beta transpose y minus x beta. This was the residual sum of squares in vector form plus lambda absolute, whatever, 2 norm square, or I could have, it's the same thing as lambda beta transpose beta. It's the same thing as sum of beta j squares. And lasso was the same thing. This is ridge, first two, and this guy is lasso plus lambda. People use this notation, but it's basically the same thing as lambda sum of absolute value. Okay. I mean, I just wrote, I'm just saying that this is the same as this is the same as that. Not a big deal. But ridge and lasso, there's a slight change in the penalty. And what is the impact of lambda? I just subjectively explain, right? When lambda is really small, you basically, these are not relevant, essentially, these terms. And when lambda is really large, these terms are very relevant. And to understand like the notion of ridge versus lasso, I think last time I said this term here, just forget about ridge versus lasso, just linear regression, the residual sum of squares in 2 dimensions, just to indicate like what's happening in 2 dimensions. There is this contour plot that I plotted. This plot is actually, what is the center of this plot? This is actually a plot in beta 1, beta 2 space. In 2 dimensions, I'm actually just thinking of the beta space. Okay. So this term is actually a score for every beta vector in this 2 dimensions. So maybe the lowest score, this thing is actually quadratic, right? This residual sum of squares is quadratic. So it's like a ball-shaped thing, okay? And you kind of compress all that, squish that onto 2 dimensions. The ball is being shown as like a contour plot, okay? With the point here being the lowest point in the contour plot, okay? And so if these terms are not there, your best solution for beta is the lowest point in the contour plot, right? That's what to minimize the residual sum of squares. Tell me the point in the lowest, which is this point. Now what these terms are doing is that I don't want to prefer this. So in general, not just these terms. So for both ridge and lasso, we had an equivalent thing where you minimize residual sum of squares of beta, which is that term. Subject to, it's a beta transpose beta is less than or equal to some budget. I think I said there is an equivalent. This problem of adding a penalty is the same as this problem with a constraint like this. This is called a constraint. Okay, we'll see constraints in SVMs later on, several lectures down the line. So this is a specific constraint for ridge. There's another specific constraint for lasso, and lasso is the same thing. Sum of absolute value of beta j is less than or equal to t. Okay, same objective. Some objective here, same objective there, and with this constraint. So first thing you need to understand is, okay, ridge and lasso have these specific constraints. Let's not worry about those specific constraints, but any constraints. What does it mean? So I have this ball. So this ball doesn't stop here. Actually, it goes on, for every beta. Right? Now constraints just mean let's say I want to pick only betas in this region. Okay. Then what does it mean? So here in this region, I only am restricting myself to this region. Then there's a beta here, which has a higher score than a beta here, which has a higher score than a beta here, right? Because we see that there's a scoring of, it's basically like restricting the view of scoring function, residual sum of squares, only to this region. So maybe you'll pick a beta which is like the lowest, the one which is closest to this guy, but in this region. That's what a constraint does. Okay. And ridge and lasso are essentially two different types of constraints. Okay. And in fact, these constraints are centered around 0. It turns out. If you want to just think of this constraint, it's actually a circular constraint in 2 dimensions. I mean, it's just a circle. That you can see, right? It's basically beta transpose beta is beta 1, beta 2. Beta 1, beta 2 is a circle T. This is the same as beta 1 square plus beta 2 square. Yeah, this is a circle T. Right? This is the equation of a circle. I mean, equality is the equation of a circle. Less than equal to saying things inside are also fine. Right? And it's centered around 0. It's a circle with center 0, 0. Right? So this is the constraint region. So where would the region be? It will be somewhere over here. Right? This is the constraint region, and there's a budget T, and this T kind of determines how big the circle is. Right? When T is large, then this like huge circle here. But when T is large, I think I told before, when T is large, it's the same thing as saying lambda is really small. So basically, you're saying when T is large, I can consider big constraint region. It's as it's really huge, and it may include this point, which means you just pick that point as the best solution. So constraints just mean in this constraint region, which is the best beta. The beta which has the lowest, like on the lowest on the contours in the contour line. Okay. And so that's what ridge is. So basically, ridge, in this example, for instance, there's maybe another contour here. So maybe we'll pick some point here. That's going to be the beta hat ridge. Okay, beta hat ridge. This point is going to be beta hat. I mean vanilla, I guess. I mean whatever you want to call it. I'm just giving useless names here. Now, is this ridge version clear? And then I'm going to tell you what the constraint for lasso looks like. Okay. Yeah, so you always want to be close. This is the lowest point. It's a ball. So what is the lowest point in a ball? The bottom point of the ball. But if you only want to consider a part of the ball, then the lowest point is some point which, if you cannot get to the bottom, there's going to be some other point. Right? That's this point. They're saying I only want to search for betas in this. That's a constraint. Then the lowest point would be something like which is going towards it, but it cannot go beyond the circle that I'm looking at.
Just to make sure I got that, if our constraint is large enough that it includes.
Yeah, if it's really large, then it will include. Yeah, that's the best solution.
And that's just linear regression.
Yeah, that's the linear regression. So when you pick lambda to really small, or t really large, then you're basically just doing. Yeah, it's just it's the original problem.
Are we given this constraint or how do we come with the
No, this is a constraint view. So the problem that you're solving is this, but this is just a saying for every fixed lambda there is a t such that this is the equivalent problem.
Yes, but where is t coming from?
You want to find t as a function of lambda? Like you want me to explicitly write what is this in terms of lambda?
So we are saying that ridge works best when the constraint is small and t is small.
Yes.
But
T is small essentially means lambda is large. You are setting the only thing you can set in ridge is lambda. Yeah. So when lambda is large, T is going to be small. I mean, this is an equivalent view. Okay. Actually, if you really want, T probably is I think c by lambda or something, some constant c by lambda. But it doesn't matter. Okay. In the sense, we haven't done any work to understand why it's c by lambda, right? I mean, in the sense of otherwise we just take it as a fact.
is it that they are inversely proportional?
Inversely related, yes. So this is ridge, okay. So we also did a ridge SVD interpretation of ridge. That's the more difficult part. But this one, this was to kind of understand comparison with lasso. Okay. So in lasso, what happens is the constraint region is actually like a diamond. Same data point, like something like this, whatever it is. Okay. It's going to be like, okay, diamond is not even going through there. It's like a diamond. Okay, that's what constraint region looks like. You can actually kind of see why it is the case. Right, the maximum magnitude is only going to be ones, right? Because some of them should be actually equal to t. So if I set everything else to be 0, one of the coordinates can be at most t or minus t. Right? So that's like these ends, and same thing on the other side, second coordinate. And in 2 dimension, it just happens to be equation of a line, beta 1 plus beta 2, absolute value equal to constant, is like these 4 lines. These are the 4 possibilities. So that's why it's like this, and then less than equal to just makes it a region. So in terms of regional space, one is a sphere, okay, with one is a ball. Actually, sphere is just a word to use just the surface of a thing, like a circle. There's a ball. Okay, ball means like anything inside as well. And this is going to be whatever, a diamond and inside, and sphere and inside. That's the search area. And the difference between ball and this guy is that lasso will, what happens is lasso intersects, basically as I said, you kind of are looking for best beta. The best beta happens to be more often than not happen to be at these corners. This guy is sharp at some edges, so best betas generally happen to be at the corners. Not always the case, but more often than not, they'll be at the edge. And what does beta at the corner mean? That means that if for example, this corner is the best one, that means that beta 1 is 0. So lasso, even though I'm solving a problem like this, is automatically setting some betas to be 0, actually, directly. Whereas ridge, most likely will never set anything with 0, but it still has a budget, so it's gonna ensure that the betas are small. Okay. But lasso is closer to a subset selection type of thing, where it's actually setting things to 0. That is the difference. Is ridge versus lasso clear? And in lasso, there's a lot more things that people do, especially lasso makes sense for high dimensional problems. High dimensional, like millions of input variables, which some companies solve, especially the online e-commerce advertising type of companies that solve really huge linear regression problems. There, I think lasso may be the tool of choice for them. And also there's for ridge there was a nice closed form expression. For lasso, I'm not sure. Maybe researchers have figured out a closed form expression, but I'm not sure about that. But there was an SVD view of ridge that was more interesting. Like just looking at ridge, it seems like all the betas are equally. You just scale down all the betas, and maybe that's the best beta you get. That's not true. You scale down different coordinates of beta in different ways. Okay, so that's the whole point, that you want to scale down some betas of the irrelevant input variables closer to 0 than you would scale down the betas of the relevant variables. Okay? The scaling down of betas is happening in different, unequally. It's not all the betas. I'm not just dividing it by some constant or something, like not bringing them down all of them in the same way. Okay? That was the SVD interpretation of this ridge regression. Did that make sense or not make sense? No. Do you want me to explain that rescaling, or given how many minutes? No minutes. Yeah, if you have, so do you want me to cover anything else, or if not, then let's break the class, and if people have questions, just come to me in the front. Okay, let me count the number of people. 3, 6, 9, 11, sorry, 12, 13, 16, 19, 23, 24, 25. So still, the class strength is 34 or something, or 36. So 10 people are missing. Or maybe, hopefully. Okay. I mean, do you see any of your group mates missing? Or all your group mates here? Which group is the best group? Which group has all its teammates in the same in the room right now? Wait, you can't. Not everybody can lift their hands. Okay, some teams don't have their teammates. Oh, okay, that's good. So maybe you can tell me that your team was here, and I can, remember that. Okay, I mean, we finished the class, so any questions you can come forward.